Previously, we talked about Max Tegmark's Level 3 multiverse and explored some of its characteristics. Today, we will be looking at the next and the final level of the multiverse, or the Level 4 multiverse, as proposed by Tegmark and some of its defining characteristics. Let's suppose for a minute that the Platonist paradigm is true, and there really does exist a theory of everything. However, we simply haven't discovered the correct equations yet. Now this raises an important question posed by renowned physicist John Archibald Wheeler. Why these particular equations and not others? To address this question, we'll need to explore the idea of mathematical democracy, where universes governed by different equations are equally real. Welcome to the Level 4 multiverse. But before we dive deeper, we need to grasp two important ideas: the concept of mathematical structures and the possibility that the physical world itself is a mathematical structure. While many of us see mathematics as a bag of tricks for manipulating numbers, mathematicians have a much broader perspective. They study abstract objects such as functions, sets, spaces, and operators, exploring the relationship between them and proving theorems. In fact, modern mathematics papers can be so abstract that you'll hardly find any numbers in them, except for the page numbers of course. But despite the wide variety of mathematical structures with complex names like orbifolds and Killing fields, there is an underlying unity. They are all special cases of what we call formal systems. A formal system consists of abstract symbols and rules for manipulating them, specifying how new strings of symbols referred to as theorems can be derived from given ones referred to as axioms. This historical development represented a form of deconstructionism, since it stripped away all meaning and interpretation that had traditionally been given to mathematical structures and distilled out only the abstract relations capturing their very essence. As a result, computers can now prove theorems about geometry without having any physical intuition whatsoever about what space is actually like. This image provides a glimpse into the vast landscape of mathematical structures and their interrelations. Although this family tree likely extends indefinitely, it illustrates an important point. Mathematical structures are not fuzzy concepts we create, but rather something we discover. They exist somewhere out there, waiting for mathematicians, computers, and even contemplative alien civilizations to uncover them. And regardless of who finds them, a theorem remains true, whether proven by a human, a computer, or an alien. Now let's explore the possibility that the physical world itself is a mathematical structure. While this idea has been traditionally accepted by many theoretical physicists, it carries profound implications. It suggests that mathematical equations not only describe limited aspects of the physical world, but every aspect of it. In other words, there exists a mathematical structure that is isomorphic or equivalent to our physical world, with each physical entity having a unique counterpart in the mathematical structure and vice versa. Let's consider some examples. A century ago, during the reign of classical physics, scientists believed that physical space was isomorphic to three-dimensional Euclidean space known as R3. They also believed that various forms of matter in the universe corresponded to classical fields such as electrical and magnetic fields mathematically represented by functions on R3. In this view, dense clumps of matter like atoms were simply regions in space where some fields were strong, corresponding to large numbers. These fields evolved deterministically over time according to some partial differential equations, and observers perceived this as things moving around and events taking place. So, could then fields in three-dimensional space be the mathematical structure corresponding to the universe? The answer is no, since a mathematical structure is an abstract, immutable entity existing outside of space and time and cannot change. Our familiar frog perspective of a three-dimensional space where events unfold is equivalent, from the bird perspective, to a four-dimensional space-time where all history is contained. So the mathematical structure would be fields in four-dimensional space. In other words, if history were a movie, the mathematical structure would not correspond to a single frame of it, but to the entire videotape. Now, what does it mean for the physical world to be a mathematical structure? Let's explore this question. If you consider yourself a self-aware substructure within a mathematical structure of our universe, then we will say that our mathematical structure has a physical existence. So what would mathematically such a self-aware substructure be like? In the classical physics example, you could be envisioned as a tube through space-time, akin to what Einstein called a whirl line. The tube's location would specify your position in space at different times. Within the tube, the fields would exhibit complex behavior, processing information about the field values in the surroundings. At each position along the tube, these processes would give rise to the mysterious sensation of self-awareness. From your perspective as a self-aware substructure, this one-dimensional string of perceptions along the tube would manifest as the passage of time. While this example helps us understand how our physical world can be a mathematical structure, it's important to note that the specific mathematical structure of fields in four-dimensional space is now known to be incorrect. Einstein's search for a unified field theory led him to propose a 3+1 dimensional pseudo-Riemann manifold with tensor fields, but even this theory failed to fully account for phenomena like black hole evaporation and the Big Bang. According to quantum field theory, our universe, which encompasses the level 3 multiverse, is better described as an algebra of operator-valued fields. However, the true mathematical structure isomorphic to our universe, if it exists, is yet to be discovered. Now let's consider the concept of mathematical democracy. If our physical world is a mathematical structure and we are self-aware substructures within it, what about all the other boxes in the mathematical tree that we see here? Do they also have physical existence? If not, it would introduce a fundamental and unexplained asymmetry into the heart of reality, dividing mathematical structures into two classes, those with physical existence and those without. To address this philosophical conundrum, Max Tegmark suggests a solution: complete mathematical democracy. According to this idea, mathematical existence and physical existence are equivalent. Therefore, all mathematical structures exist physically as well. This concept gives rise to the level 4 multiverse, which can be seen as a form of radical Platonism. It asserts that mathematical structures, similar to Plato's realm of ideas or the mindscape of Rucker, physically exist somewhere out there. This aligns with the modal realism theory proposed by David Lewis, but now in mathematical terms. According to this theory, an infinitely intelligent mathematician could derive all properties of parallel universes, including the subjective perceptions of all self-aware substructures within them. Now, since we have described the 4 levels of parallel universes in order of increasing speculativeness, why should we believe in a level 4? Well, logically, it rests on 2 assumptions. The first assumption is that our physical world, specifically the level 3 multiverse, is a mathematical structure. The remarkable usefulness of mathematics in describing the natural sciences supports this assumption. Our successful theories are not mere approximations of physics, but mathematics approximating mathematics. As physicist Eugene Wigner noted, the enormous usefulness of mathematics in the natural sciences is broadening on the mysterious. It suggests that mathematics and the physical world are deeply intertwined. The second assumption is mathematical democracy. Abstract mathematics is incredibly general, capable of defining any theory of everything defined in purely formal terms. In other words, any conceivable parallel universe theory can be described at level 4. This idea brings closure to the hierarchy of multiverses, leaving no room for a level 5. It implies that all mathematical structures, even the ones we haven't discovered yet, exist physically. This provides an answer to Wheeler's question: why these particular equations and not others? The answer lies in the inherent richness and diversity of mathematical structures. Now let's explore what level 4 parallel universes might be like. In a multiverse theory, there are multiple self-aware substructures that have experienced identical past lives to yours. Determining which one is you becomes impossible. However, we can still make generic predictions based on observations and probabilities. Prediction 1. The mathematical structure describing our world is the most generic one consistent with our observations. It means that our universe is not a special case, but rather a representative example of the mathematical structures in the Level 4 multiverse. Prediction 2. Our future observations are the most generic ones consistent with our past observations. And Prediction 3. Our past observations are the most generic ones that are consistent with our existence. The genericity of mathematical structures often leads to symmetry and invariance properties, contributing to the simplicity and orderliness of our universe. These properties are widespread among mathematical structures, making our universe just one among many in the Level 4 multiverse. And that concludes our exploration of Max Tegmark's Level 4 multiverse. We've journeyed from the abstract world of mathematics to the profound idea that our physical world is a mathematical structure. We've pondered the concept of mathematical democracy and the existence of parallel universes. The Level 4 multiverse presents a radical yet intriguing perspective on reality. But keep in mind that the universe holds countless mysteries, and we're only scratching the surface. If you enjoyed this video, do leave a like, share, and subscribe to our channel for more content ahead. Also, let us know your thoughts in the comment section down below. Until then, we'll see you in the next one.